Hello students, in this video we'll compute the Fourier series of a step function and infer some interesting results about infinite series from that function. Let's define f of theta to be equal to 1 for absolute value theta less than some number delta, which is going to be less than pi, and 0 else. Make this function 2 pi periodic by doing this, saying that f of theta is equal to f of theta plus 2 pi. That periodizes the function. And then let's find the Fourier coefficients of this function. Let's find the Fourier series of this function. So find the Fourier series of this function. Okay. All right, so let's do it. So what's the let's first compute the 0 Fourier coefficient. So the 0 Fourier coefficient, f hat of 0, is 1 over 2 pi, the integral from negative pi to pi of the function f of theta, and then e to the negative I times 0 times theta, right? d theta. So this is just going to be a 1 over 2 pi. I integrate from negative delta to delta, because that's where the function exists, of just 1. So I have a d theta. So the 0 coefficient is just going to be a delta over pi, because I have 2 delta over 2 pi, delta over pi. Now let's suppose that n is not equal to 0. Let's find the non-zero modes of this function over here. F hat of n is going to be, by the same reasoning, 1 over 2 pi, the integral from negative delta up to delta. That's where the function turns on. And then 1 times e to the negative I n theta, d theta. So these are going to be common calculations of the Fourier series. I'm going to have a 1 over 2 pi, and then I'm going to have a e to the negative I n theta over negative I n from negative delta up to delta. Of course, what we'll get over here is we're going to get 1 over 2 pi I n. And then with this negative sign over here, I'll get rid of that negative sign by flipping the limits. So I'm having e to the I n delta, and then minus e to the minus I n delta over here. And so now let's examine these coefficients carefully. Notice that I have a 2 and an I, and an e to the I something and a minus e to the minus something. Now that's our definition of sine. So recall that sine of x, if I complexify it, is e to the ix minus e to the minus ix over 2i by Euler's formula. So what I have over here is I have exactly just the sine of n delta over what? Over a pi times n. So pi times n. So now I have our Fourier series. Our Fourier series, our function, f of theta, is therefore equal to what? Since the function is smooth, except for the points negative delta and delta, its Fourier series is going to exist and it's going to converge to the function. It's going to be the 0 mode, just a delta over pi, that's the 0 mode, plus the non-zero modes, n not equal to 0, of the Fourier coefficient sine of n delta over n pi, e to the I n theta, like that. That's our complex Fourier series. All right, and so I know this Fourier series is going to converge to the value of the function at the origin, because the function is smooth at the origin, or in a neighborhood of the origin. So I can plug in 0 to this function. If I plug in 0 to this function, I get that 1 is equal to what? The function when theta is equal to 0 is 1, is going to be a delta over pi plus the sum over n not equal to 0 of the sine of n delta over what? N pi. Now, of course, I can symmetrize this, because I know that when I plug in the negative numbers over here, if I have a negative n, it's the sine of negative n and a negative n in the denominator. The sine's an odd function and n's an odd function, so the quotient is an even function, so I can symmetrize over the negative and positives and write this as equal to delta over pi plus 2 times the sum. N goes from 1 to infinity, the sine of n delta over n pi. By symmetry? Okay, great. And so now I can solve for this series over here. So if I solve for this series, notice there's a pi over in the denominator, so I'm going to multiply by pi, subtract delta, and divide by 2. If I do that in sequence over here, so multiply by delta, multiply by pi, subtract delta, and then add 2, I'm going to get pi minus delta over 2 is the sum. N goes from 1 to infinity of the sine of n delta over n. Okay, great. We get this relationship over here. That's our first relationship. We get this awesome collection of infinite series using our Fourier approach. And now what I can do is I can also use the Parseval result. The Parseval result says that if I take the L2 norm of the function and square it, that has to be the sum of the square of the Fourier coefficients. So what's the L2 norm of this function squared? 1 over 2 pi. It's only going to turn on between negative delta and delta. And then I just get a 1 squared, which is just 1 d theta, right? So this is going to be a delta over pi. That's the L2 norm of the function squared. And now, of course, this is the sum of the square of the Fourier coefficient. So what this is going to be is this is exactly going to be the 0 coefficient squared. So that's going to be a delta squared over pi squared. And then plus the remaining coefficients over here. So I'm going to have these numbers over here squared over here. So these are my Fourier coefficients. I'm going to square these things. I'm going to do the same symmetry trick, right? So I'm going to have plus 2, the sum, n goes from 1 to infinity, of the sine squared of n delta over n squared pi squared, right? And so now if we actually, what we can do is if we algebraically solve this expression, what we'll find is the following. We'll also get this relationship. This will imply that the sum, n goes from 1 to infinity, of the sine squared of n delta over n squared delta is equal to the same thing, is equal to pi minus delta over 2. If you just do the algebra and solve this equation for the corresponding result, and you'll get this. Excellent. And so now, what's one really neat application of this formula over here? So if I plug in delta equals, if I plug into this formula delta equals pi over 2, what we're going to get is the following. We're going to have the sum, n goes from 1 to infinity, of the sine squared of n times pi over 2, over n squared is going to be equal to what? Well, if delta, I'll have a pi over 2 over here, and this is going to be a pi minus pi over 2 is pi over 4. So this whole thing, if I multiply by pi over 2, would be a pi squared over 8. Now, of course, when does this turn on? Only time this turns on, now if n is an even number, the numerator is going to be 0. If n is an odd number, the numerator is going to be 1. So I can conclude from this, is I can conclude that the sum, n goes from 1 to infinity, of when n is an odd number, the numerator is equal to 1, so I can just sum over the reciprocals of the odds. So the sum of the reciprocals of the squares of the odds is equal to pi squared over 8. Okay? And now I can use this formula over here because I know that if I sum the square of the odds and I do twice the sum of the square of the evens, reciprocals of the evens, I get to all of them, right? And so this allows me to conclude, and this is a good exercise, use this result over here. And so you can write the sum of the odds and the sum of the evens can be compared to the original sum of the squares. We can conclude this over here, that the sum, n goes from 1 to infinity, of 1 over n squared is equal to pi squared over 6. And that's, of course, our Riemann zeta function at zeta equals 2. In further videos, we'll see how to generalize this formula to zeta of 2k, where k is any integer, by using the Bernoulli polynomials. Thank you very much.